Hi everyone, in the previous lecture we discussed search agents or planning agents that aim to find a solution to a problem, and this solution is often expressed in the form of a sequence of actions, for example to go from point A to point B, from city A to city B. In this lecture we discuss another kind of search that's as important in artificial intelligence, and this search is called adversarial search. So you have guessed, adversarial search problems are also known as games. They occur in multi-agent competitive environment in which there is an opponent who is actually planning against us and that we can't control. To clarify again the concept of game versus the concept of search, in games we look for the optimal solution, which is not, as I said, a sequence of actions anymore, but a strategy or policy that help us win the game. If the opponent is doing A, then we do B. If the opponent is doing C, then we do D. So we could express that as a set of rules if we implement it with rules. However, it's tedious and hard if it's hard-coded this way. So we need to find a way to devise an intelligent system that actually help us play and win the game against our opponent. So the good news is that to devise such a games, we are going to only reach to two kinds of ingredients that you know already, which are search problems, algorithms, and also heuristic evaluation functions. These are the two main ingredients to help us model and solve games in AI. I would like to mention first that games are considered as a hard topic in AI. It's a hard and hot topic that actually pushes the boundaries of research in AI. So it's a big deal. They are interesting from the AI perspective because they are too hard to solve. So for example, chess, which is considered as a complex problem to solve for human and also for the machine, has a branching factor of 35, which means that the search space to explore is of 35 to the 100, which is approximately 10 to 154 nodes. That's a huge space to explore. So we need to make a decision even when the optimal solution or decision is unfeasible. This means that actually we really need to reach out to approximation is a key ingredient to solve games in AI. So we need to do approximate. It's really not feasible to solve the problem by searching the whole search tree of this huge number of nodes. Historically, there have been several attempts to solve complex games such as chess, Go, checkers, etc. So for example, for checkers, in 1994, the system or the computer, or call it the intelligent agent Chinook, ended 40-year reign of human world champion Marion Tinsley. And at this time, it was actually, checkers were actually considered as a completely solved problem. It used a lot of different strategies to search the search space, going top down, bottom up, but also it used an endgame database that actually stored a perfect play for all positions involving 8 or fewer pieces on the board, a total of about 443 billion positions on the board. The game that attracted most of the attention from the AI community is probably chess. Chess is a complex game for both machines and also humans. The task was suggested by Claude Shannon in his seminal paper, Programming a Computer for Playing Chess in 1949, in which he suggested chess as an AI problem for the community. But he also laid down the background for solving games that was actually very useful in many other applications and games. He typically invented the minimax algorithm and suggested heuristic evaluation functions that actually help cut off the search space and not go up to the tree of the space. Another important moment in the history of chess in AI is when Deep Blue, the IBM intelligent machine, defeated human world champion Garry Kasparov in a 6-game match in 1997. After the match, Garry Kasparov actually expressed that he has felt deep intelligence and even creativity in Deep Blue moves. A last event in the history of chess and AI, just to cite a few, is when the undisputed world champion Vladimir Krapnik lost against Deep Freeze, the IBM machine, in 2006. But there have been a lot of other events in chess, around chess and AI. Another complex game to mention is the Go game that actually, until quite recently, was considered as intractable by AI because of its huge search space. Indeed, the branching factor for Go is over 300. However, the good news is that this year, the Google DeepMind project AlphaGo has actually beat both Fan Hui, who is the European Go champion, and Lee Sedol, who is the world's best player. A last game to mention that's not as complex as Go and chess And the checkers, it's called Othello, who is actually, for which there are several computer Othellos existing, and human champions refuse so far to compete against computers because they are too good. So Othello is also another solved game, and that actually performs better than humans. So in AI, we classify games along different dimensions. For example, if the game we have perfect information, such as looking at the whole board, we call it a game with perfect information, and this includes chess, checkers, Go, Othello, backgammon, and Monopoly. If we don't have a perfect information, which means that we don't have a whole picture of what's going on, such as our opponent has his card and we can't see them, we talk about games with imperfect information. And this includes Battleship, Blind, tic-tac-toe, bridge, poker, Scrabble, nuclear war, etc. We also talk about deterministic game versus non-deterministic games that are actually mentioned here as chance. So these are here non-deterministic games, are also called stochastic games, which means that there is a factor of chance that is being introduced, and this factor of chance is either introduced by shuffling cards or by rolling dice, etc. So deterministic games that are actually have perfect information are chess, checkers, Go, Othello. Those with imperfect information are Battleship, Blind, tic-tac-toe, etc. Those who are actually perfect information and chance are backgammon and Monopoly. Those who involve both imperfect information and non-deterministic or stochastic search are bridge, poker, Scrabble, nuclear war. In this lecture, we are mostly interested in deterministic games that are actually fully observable environment or with perfect information. These are hard enough. We call them also zero-sum, where two agents act alternately to play the game. We are going to touch a little bit on chance afterwards, just to give you an idea of how this actually changes from deterministic case. Zero-sum games are typically adversarial games that actually involve pure competition, where agents have different values on the outcomes, and one agent is trying to maximize a single value, while the other agent is trying to minimize it. Each move in the game by one of the players is called a ply. So we have here one objective function. One of them is maximizing it, and one of them is minimizing it. So this is what we call zero-sum games. Zero-sum game involves what we call embedded thinking or backward reasoning, in which one agent is trying to figure out what to do, how to decide. He thinks about the consequences of his actions. He needs to think about his opponent as well. The opponent is also thinking what to do, and so on and so forth. Each will imagine what would be the response from the opponent to his or her actions. This entails embedded thinking, and we need to take that into consideration when we solve the problem. We can formalize the problem as follows. So we start with some initial state. Let's call it S0, so for example. So we start with some S0. Then player of S defines which player has the move in state S, usually taking turns. Actions of S will return the set of legal moves in S. We're going to define a transition function that goes from S cross A, the set of states across the possible actions, to S, which defines the results of a move, and define a terminal test, which is true when the game is over or false otherwise. States where game ends are called terminal states. We're going to define another function called utility, SP, that actually is a utility function or an objective function for game that ends in terminal state S for player P. In chess, the outcome is either a win, a loss, or a draw with values that could be +1, 0, or half. For tic-tac-toe game, it can be a utility of +1, -1, or 0 if it's a win, loss, or draw, respectively. So this is how we formalize the problem. So first of all, let's think about having a single player and how does it work. So first of all, we assume we have a tic-tac-toe game. That's one of the simplest games with one player. So let's call this player Mr. Max. Okay, so Mr. Max has the play, and we ask him to play 3 moves only for the sake of the example. So Mr. Max is going to play the game and put some crosses on the board. So he could do something, for example, like this, 3 moves. And we could declare, okay, so you win, Mr. Max win, and this is a possibility to solve the problem when he is only by himself and there is no opponent that is actually against him. So let's examine what the search space looks like. So Max is going to start the game. The initial state is S0, in which the board has 3 by 3 cells. So Max can put the cross anywhere, which represent actually 9 possible actions. So this is a branching factor initially of b = 9. So Max could put the cross here, here, or anywhere in the board, in any of these children. So suppose Max picks to put the cross here, then the second step is for Max to put a second cross, and this cross could go anywhere in the remainder 8 positions. So suppose Max picks this position here. So then Max could put the cross here and win the game, or he could put the cross here or here and not win the game. So remember that we are asking Max to put only 3 crosses on the board. So if he puts the cross here, he will end up with a utility of +1 and 0, otherwise if he doesn't actually manage to put the cross to make a straight line. So in the case of one player, nothing would prevent Max from winning. That is, choose the path that leads to the desired utility of 1, unless there is another opponent or player who will be doing everything to prevent Max from winning. Let's call him Min, the mean. So we are going to, in this case, to have a configuration of what we call the mini-max search algorithm, in which we have 2 players, Max and Min. Players alternate turn. This is the true game. There are 2 players in tic-tac-toe. Players will alternate turns. Max moves first. Max maximizes the result, and Min tries to minimize the result. There is one objective function or one utility. Max maximizes it. Min minimizes it. Then we compute each node the minimax value that is the best achievable utility against an optimal adversary. Minimax value is the best achievable payoff against the best play. So we suppose that both players are playing the best play. They know very well tic-tac-toe, and everyone will do his best to prevent the other one from winning. So now the search space is turning something different. Now we don't have anymore only Max playing. We have Max, and so Max is here, right? And then we have also Min, who is actually trying to prevent Max from winning, and Min is actually acting against Max. So we have a layer of Max, layer of Min. We call each layer, we call it apply, right? And we're going to try to go all the way down until we have actually Max win. So Max starts first. He will put a cross. Then Min will have different actions to do. He will be putting a circle and preventing Max from winning. So suppose that Min puts his circle here. Then Max plays his turn, and he will be preventing Min from winning by putting the cross here, and so on and so forth. So we have now a whole such plays that are actually different plies. Each ply is for one of the players. So this is player 1, player 2, player 1, player 2, and so on and so forth. And again, there are terminal nodes that actually are either in which we have Min winning or Max winning, or it's a draw in which none of them is actually winning. So this is the whole search space of possibilities for Max and Min taking turns and playing tic-tac-toe. So the adversarial search for the mini-max algorithm works as follows. It aims to find the optimal strategy for Max to win. The approach is a depth-first search, which you know from the previous lecture, of the game tree. So we have a game tree just like the tic-tac-toe, and we're going to adopt a depth-first search in which an optimal leaf node could appear anywhere at any depth of the tree. The minimax principle computes the utility of being in a state assuming both players are playing optimally from there until the end of the game. So both tic-tac-toe players are really doing their best. They're not making any mistake in their playing. So the idea of minimax algorithm is to propagate the minimax value up the tree once terminal nodes are discovered. So this entails that we are going actually to go all the way down the tree and down to the tree, the leaves in the tree. So this entails that we're going all the way down in the tree. So the idea of the minimax can be summarized with these simple if statements. If the state is a terminal state or terminal node, then we're going to just uncover the utility of the state. So the utility of the state is the number that we are going to give, in depending on whether the state is in favor of Max or not. If the state is a Max node, then the value is the highest value of all successors of node's children. So again, to call minimax again here, it's a recursive function that actually is going all the way down to get the maximum value along that path. If the state is minimum node, then we are going to reach for the lowest value of all successors node that are the values, all the values of the children. Remember, Max tries to maximize the objective function, and Min is trying to minimize it. So that's why we are going to reach here to get here the highest value of all successors if it's Max, and the lowest values of all successors if it's Min. In other words, the minimax of a state S is given by the utility of S, or the value of the objective function at S, if the terminal test of S is true. So we reach the terminal state. If it's Max, plane, then we're going to maximize all the children value. So we're going to call recursively minimax of the results of applying the action S for the state S. We're going to do that over all the actions and take the maximum over the path of all the actions for S. If the player is min, then we're going to call minimax recursively with the result of applying the action A for all the actions on S. So we're going to take the minimum of the resulting from the minimax of all of those actions for min. This is how we apply. It's a simple recursive algorithm that will actually try to find the minimum over the path for min and the maximum over the path for max.